Okay, so in this function of temperature versus time, since we took the bread out of the oven, is it constant rate of change? Do we have constant rate of change? Okay, are we listening, or are we working on the smartphone, or what are we doing? Okay, smartphone's away, okay? And if you need to close your screen, that's too tempting, close your screen, okay? All right, so do we have constant rate of change or not? Okay, so I heard a no. So someone said no. Why no?
Because the moment that it changes in is too big.
Um,
Like the dx of 2 is too big of a moment.
Yeah, sorry. Did I say something about a moment? So what? The question was, is that function g? Is it constant rate of change? Is it constant rate of change? And you say no because it's curved, right? It's curved, right? So you look at this whole thing. It curves. It's not constant rate of change. But
at the section around, that starts around, we'll say about 32, 33-ish on the X, from that moment on, the line looks almost linear.
Okay, so he's saying this part we can maybe consider constant rate of change over here. What about over here? Do we have constant rate of change over here?
An infinite number.
Okay, so in the general sense, no, it's curved. But our whole point here is that if we zoom in close enough and we get a small enough moment, that the graph will essentially be linear. So it's kind of it's yes and no, right? So it's no in that in the broad sense, it's a curved graph, and so there's not constant rate of change. But if we zoom in close enough on any particular place until it's linear, then in that particular moment we can assume it's essentially constant rate of change. Okay, and then when we have that in that small interval, that moment, we have that constant rate of change, then everything we've worked on this semester applies. Everything about what dy equals mdx, and then building the equation like you did for your homework, right? You built, or we've been doing it over and over again now, the last 3 classes. We built the relationship for all points along a line, right? We call it the point-slope form. So that still applies. It won't apply to this graph as a whole, but it applies in a very small interval. So here I'm zoomed in here at 4.753. So at 4.753, and I think you had some exercises like this in your homework, right? Something that looked like this. So let's do this for the baked bread. So at 4.753. I'm going to zoom in on that. And so right now I'm showing dx equals 2. And it's actually showing dx from our 4.753, it's showing dx extending out one value of dx to the right and to the left. Okay, so this is actually looking at this interval within the moment is 2 dx. Right, so this is dx here. And this is dx here. So this interval from here to here is actually 2 dx. Doesn't phase us, that's fine. No big deal. Okay, so in this interval of 2 dx, do we have rate of change in a moment? Yes or no? No, because that red, the red is as a line. The black is the actual graph of the curve, and it's not essentially straight, right? It's not essentially straight. So let's try dx of, say, 0.5. So if I come up here and change dx to 0.5, and now we'll zoom in on that. And now I have a new dx of 0.5, and I'm going 0.5 to the right and 0.5 to the left. Okay, it's better, but it's still not in that interval of 2 dx. We still see that it's still curved away from that line. So we'll try 0.1. So here's 0.1, try that. What about now? Okay, it's looking, this would, be good enough for government work, right? This is like pretty close now, right? It starts to deviate away out here at the edges, but if we just keep it to this interval here, dx of 0.1 and dx of 0.1. We could say that interval there, we have a constant rate of change. And so then now within this interval in this moment at 4.753, we could say that dy equals mdx. We could also build, so say from here to here, we could build all the points on that line as y equals what, m times x minus 4.753 plus, represent it. How can I represent that value right there? How can we represent y initial? What is that? You should be thinking g of 4.753 be our initial. And that could represent every correspondence point in this moment because we've got a small enough interval, right? So all of our linear stuff applies. This is what calculus is about. It's applying essentially the mathematics of linearity or constant rate of change in very small intervals. Okay? So we come up here and get what that is. So up here that's calculating. It's taking what? It's taking the y final, g of x naught plus dx, which is the y final here, minus y initial will be the y here, over 2 dx. So it's change in y over the change in x. And we see it's negative 27. Negative 27, and what is the units on that? Degrees Fahrenheit per minute. So now, tell the person next to you, so that number is negative 27.06. Tell the person next to you what the meaning of that number is. Negative 27.06 degrees Fahrenheit per minute. Go. Okay. So volunteer, someone for whom the light bulb has just come on recently. Tell me, someone who's the light bulb's come on recently, what does the negative 27 mean? What does the negative 27? Don't be shy. How about you? You kind of, yeah, with the bottle and the glasses. Oh no, no idea. I think you've known for a long time. How about right here in the blue shirt and the yellow? Yeah. Really good. And notice, hey, he started with something different than we've had before, right? There's something different to this. That yes, for any change in time, the change in temperature will be negative 27 times that change in time. But what? Only in this moment. Only now in this moment where we've assumed essentially that constant rate. Go to 4.92 minutes. You have a different constant rate, so that doesn't apply anymore, right? That constant rate doesn't apply anymore. So yeah, so now when we talk about the meaning of a constant rate of change, it's the same as before. Changes in y are that value times change in x. But for that particular value of m, it's only in that moment that this holds true. You move to a different moment, you got a new value of m. Okay? Really important, okay? So this is what calculus is about. It's about everything we've worked on with constant rate of change and linearity, but only assumed now in small intervals, right? You move to a different interval, you got a new constant rate of change. Okay, so back to How about this? Do we have a rate of change at every moment for the baked bread example? Do we have a rate of change at every moment? If so, I'm asking if we were to pick any point on that, any correspondence point in that graph and zoom in, will we get linearity? Yes. Okay, it's a nice smooth curve everywhere. It's continuous, nice and smooth, right? So we have rate of change at every moment. Okay. What about this graph? So you should have read about this. You read about this? So here there's a particular value, right, where we don't. Because no matter how much I zoom in on that, I can't get it to be linear around that point. It will always be a sharp corner. So there is it does not converge upon a linear value for which we can calculate dy over dx, and that would hold for all values in that moment, right? What about right here? Yes, okay, right there, fine. But if the moment is at that corner point, we can never zoom in far enough to get it to be linear. dy equals mdx will not hold because of that point. All right, and so then we've got so when you have it's called a cusp. At a cusp, you don't have rate of change in a moment. So here's a very interesting function. See that it's somewhat jagged here. So if I come here and I go, say, to I can't remember what it was, 1.23. Yeah, 1.23075 is a good one. Let's see. Can you get it? We'll just try that. Okay, so let's look at this point right here. So our goal is to see, do we have rate of change in a moment here? So I'm gonna zoom in here, and we're looking for just things to smooth out and flatten out. Okay, ready? Here we go. So let me just do this one time. So what do you expect that rate of change to be? Positive or negative there? Looks like it might be negative. So when we zoom in there, we're gonna see that this thing's gonna smooth out and give us a negative rate of change. Okay, so I'm still zooming in there. Okay, so we're almost there. Still getting there. Wait a sec. All right, so what happens, no matter how far I'm zooming in here, so I was looking for an example, so there's places where you go where it looks, you zoom in like 5 or 6 times, it looks negative, and all of a sudden, then you get a place where it looks positive. So I don't have that particular place. Maybe here, let's try this. Yeah, so I found the end. Okay, but so here's the example. This is kind of the idea of a function that no matter how many times you zoom in, you just keep getting this jaggedness. You keep getting these corners everywhere. Okay, so it's the example of a function that doesn't have a rate of change at any moment. You keep zooming in, and it keeps having a corner or a jaggedness at every single point. So just to give you some contrast to the nice types of functions that we'll be using all semester, which will have rate of change at every moment, right? There'll be curves, you can zoom in, and you'll be able to get linear functions. There are functions that exist where you keep zooming in, and it's like there's a corner point everywhere, okay? There's like a corner point everywhere, all right? So just for contrast's sake, functions that don't have a rate of change at any moment. Okay, so you've got, let's see, we were talking about last time. We were working on Usain Bolt. Okay, Usain Bolt. And here is his, this is a graph of his time elapsed since the start of the race. And the y value, the dependent variable, is his distance from the start. Okay? So this is a model of that. And so what we want to do is we want to, so what kind of function is this? So this is the idea of a function that's just giving us a quantity, right? A quantity, his distance from the start, as a function of his time since he started the race. So I want to know, say at this point right here, 6.6, I want to know what is his rate of change of distance with respect to time? What is his speed? So how can I find out? So does he have a speed at that moment? Does he have a rate of change at that moment? How can I find that out? I want to. So tell the person next to you, how would I go about figuring out what his rate of change of distance with respect to time or his speed would be at this moment? Tell the person next to you. Go. Off the top of my head. Okay. So what's the first thing we should do? So I heard a lot of you say it. First thing we should do is, if I want to be able to, I want to figure out what his rate of change of distance with respect to time is at this moment. What should I do? I need to zoom in, right? I need to zoom in. Okay, so I'm gonna do that. Until what? Yeah, so we're looking for it to be essentially linear, and when you see that in this file here, you see that I'm ready for that. And that was something you couldn't see before, but so I'm showing here at 6.6 seconds. So what am I showing? I'm showing I've got a moment now. Maybe this is the moment from 6.56 seconds to 6.66 seconds. So maybe my moment is let's go 6.58 to 6.63. There's no one correct answer here, right? There's no one correct answer for what the moment is. It's just anything small enough so that it's apparently linear, and our changes are gonna fit within that. Okay? So there's no correct answer. But the key is it has to be an interval. It's an interval. It has a starting value and an ending value. That's what moments are. Okay, so then within this moment, I'm showing a dx of 0. Now, I can change that, but the way I've got it set right now is at 0.0165. Okay, and we know that this is for x equals, talking about the moment at x equals 6.6. Okay, so I want you to represent exactly the coordinates of those 2 points. Go. Represent exactly the coordinates of those 2 points. represent both of those points exactly. And then when you're done with that, once you've represented those 2 points exactly, I want you to express, don't do any calculations, express the constant rate of change here at the moment 6.6. So write down those two, express exactly. So there's no calculations involved here. You're just writing down things without doing any computing. The coordinates and exact representations, and then an expression for that constant rate of change. Okay, coordinates of the first point. How about on this side, in the back? What are the exact coordinates of this point right here? Anybody? Okay, how about in the middle on this side? Do you know? 6.6, good. He wants f of 6.6. Agree? Yep. And we can find that value, no problem, right? But we can also express it just easily, just express it, right? We know how to find it, it's fine, but the beauty of function notation is we can just express it without doing all the work. Okay, how about the second point now? So coordinates of that second point, this side, in the middle. Yeah. Oh, I like that she said plus. I like that. Okay, 6.6 plus 0.0165. Good. Good. Right, so now the new x coordinate of that point is dx greater than 6.6, right? So add dx, and then the corresponding distance at that time is f of that independent value, f of that, which is f of the 6.6 plus the dx. Okay, and then so what is now m of 6.6? Or not of, but I'm just denoting here the constant rate of change at the moment 6.6. How would we write that? So we'll actually do the addition now, okay? Good. And that's just dx, which is what? So that denominator is just dx. So, which is just the 0.0165. Okay, and so let's let GC do that work for us. And when we do, we get 12.3958, and that is, I believe that, this is got to be feet per second, right? Is this feet? No, meters per second. So we're into the middle of the race here. Probably maybe this is his top speed here. 12 meters in a second. That's insane. That's like 40 feet in a second. Crazy. Okay. So that was a lot of work just to get that one value, okay? But we should understand it to understand what we're doing there. We're just getting the rate of change at that one moment, 6.6. Go to 6.8, and we have to do it again. And so this is what your sheet is about. And you also go to Blackboard, and let me show you in Blackboard. First, any questions on this? Any questions about what we just did? Given the distance time function, we found the rate of change at one particular moment. We zoomed in, we got two correspondence points in the moment, and then we took change in y minus change in x, and we used function notation to represent that. Okay? So that's a summary of what we did. All of that's really important. So if you go to Blackboard, I've posted something for you to download to go along with that worksheet. In the lecture handouts and files, should be the first thing popping up there. So the worksheet doc file, I just gave you that. That's just for reference later. If you want to print another one out, we need the GC file. We want the GC file. So print out the GC file. And when you open that up, it should look like this. Okay, so before you start getting, so everyone got this? So let me just kind of give you an overview. There's lots of details in this, but I just want to make sure you have the big picture involved, or in mind. So what we did was, we just found the rate of change at one particular moment, 6.6 seconds. Do I have everyone's attention? We just found the rate of change at one particular moment, 6.6 seconds, okay? Now what we want to do is we want to kind of devise or we want to build a rate of change function. So you read about rate of change functions over the weekend, right? So we're going to build a rate of change function for Usain's race, okay, for his race. And so we're somewhat going to do that one point at a time, and we're going to let GC do the heavy lifting for us, okay? So you're going to follow the instructions. So the instructions in the GC file are compatible. They're aligned with the worksheet. We should have this down. So defining a function and then graphing a part of it, right? Defining a function, graphing a part of it means we use y and x to denote what we want to graph from 0 to 9.58. Okay? So now these 2 points, and these 2 points, these are generic. For any given value x equals c, what are our 2 correspondence points? And these 2 points, that corresponds with the header row, right? What you're putting in the header row above the actual rows of the table. So what's our first correspondence point at x equals c? C and f of c. So think of c like a parameter. X is your variable, and c is like a parameter. So for a given situation, we're looking at that particular value of x, and that's like a parameter then. Okay? So c and f of c, and then the other, so now we need another correspondence point in the moment at c. So what's its x value? He wants c plus dx. Agree with that? That's right, c plus dx. Right? We know dx necessarily implies that you have rate of change at a moment. You have rate of change. So that dx is going to be inside a moment where we have rate of change at a moment. Okay, and what's the corresponding y value? Oh. We just need the y value for that x value, right? So it's going to be f of c plus dx, right? So this is what you should have put in your header row above the main part of the table. The first correspondence point is c f of c. Second correspondence point, c plus dx, f of c plus dx. So it's just like our example for 6.6, but now we're just letting that 6.6 be any value of focus, and then the dx can be variable too, right? So the dx can be variable too. So that's the header row, okay? Then the next thing is to define in GC a formula that's going to now calculate the current value of m. So we want to use our correspondence points to get the current value of m. What will it be? Change in y, which is y final minus y initial, divided by change in x. So c plus x minus c, right? That works, or we could just write, what's the change in x? Dx. Not there. So yes, you could write c plus x final minus x initial, but what we're setting up an expression for is the change in x. So you could just write dx because that's what it is, and that's what you get when you subtract c plus dx minus dx. Yeah, f of c. Thank you. If you were a student thinking that, you should have talked up, spoke up. Yeah, you notice. You give extra credit for that. If you notice me making a mistake, speak up. Okay? So yeah, f of c plus dx minus f of c. I was going too fast. All right, so now you're ready for 1b, which is one row at a time. You're going to make this table, but because we've just set up this is going to, as soon as we have a value of c and dx, it's going to just give us m. We don't have to do any punching, right? It's going to give us m for any value of c and dx. So come in here and do, let's do, how about 5.0 together? So if I come in here and do 5, so now I've got that point. So let's zoom in to see how far we need to zoom in to set dx so we're in the moment where we have rate of change at the moment. So to zoom in, to make a box, so you can do shift and make a box like this. If you're holding down shift while you make a box, it'll zoom in on that. Okay, so then we can vary dx if we need to. So everyone could have a different dx for these. So for every value of c, you're going to vary dx so that it's inside your moment and it looks reasonable. So here we have a moment where we've rate of change in the moment because we're essentially linear. So my dx here now is 0.002, c equals 5. Based on those two values and the calculation for m above, it's automatically cranking out that value of m, 11.9. So in your table, if you did this, so you might have a different dx. So my moment would be, say, 4.985 to 5.04. Okay, I could write that interval. You could have something slightly different. dx I have set to 0.022. My first correspondence point would be 5 f of 5 and 5.022 f of 5.022. And then m, we've already put up here, we already put the formula for m. We're letting GC do it for us, right? We're letting GC calculate dy over dx, and it's giving me 11.902. 002. So then I would put that over there on the right. Okay, so maybe just do a couple more rows of that, but let me just tell you where you're going with this. So as we do each row, what are we doing? We're finding the rate of change at each of these moments. 0.5, 1, 2, 2.5, 4, etc. So we'll have like 10. We'll have 10 rates of change throughout his race, right? We'll have 10 rates of change throughout his race down that last column on the right. And so now, using the very first column on the left, here's the key to this whole thing. Using the first column on the left as an independent variable, same as the one we have here. And now using this last column as the right as a new dependent variable, rate of change, we've got correspondence points of time since start and rate of change. We've got 10 of them. So we're going to plot those correspondence points down here, and now what are we doing? We're building what's called a rate of change function, where the dependent variable is now no longer distance, but rate of change of distance. See? So we're building a new function out of the original one. So we've got this distance function. By finding all these rates of change, we're building a rate of change function. The dependent variable now is rate of change. So you're going to do that by plotting those correspondence points, and then assuming that there's going to be ones all in between there. It's going to connect the dots, right? Connect the dots to represent all possible correspondence points. And that's the idea of a rate of change function. So maybe do one more row in the table.